Assalamualaikum warahmatullahi ta'ala wabarakatuh and salam sejahtera. Okay, today video session is supposed to be a tutorial session, so focusing on problem related to Ampere's circuital law. So we have done 3 examples in my previous lecture regarding ACL. Now I'm going to continue from there. So therefore that's why we start with example number 4. And we're going to do problems that we have seen before in Biot-Savart law. So therefore, we're going to do this problem because we have done it in Biot-Savart law. And this problem actually taken from our Sadiku textbook, practice exercise 7.4, where you've been given a solenoid, okay, a solenoid, and the structure as shown, radius A, length L, and the number of turns is N turn, and each conductor carrying current I. And then we managed to find the magnetic field intensity along the axis of this solenoid. That's what we have done in that problem. So now we're going to use that as our foundation for problem related to Ampere's circuital law. Yeah? Okay, so let's state the description of the problem here. We slightly change it so that it's suitable for the application of ACL. So just state this, we add this new information. Let L, which is the length of the solenoid, is much greater than A, which is the radius of the solenoid. Find H, and H known as magnetic field intensity in the region center of the solenoid. Okay, in the region center of the solenoid. So what does it mean? We want to find what is the H located at this region. Okay, that's what we're going to determine here. I'm going to explain why, because we are focusing this problem for ACL method. So that's why we have to have this condition in order to justify us using ACL as the approach to solve this problem. Okay, so that is our problem. Now we slightly changed compared to the previous problem that we did in Biot-Savart law. Okay, since we have done it using Biot-Savart law, it's much better for me to recall it, and then we try to find the solution based on that method, and then we're going to solve this problem using ACL, and then we're going to compare both results. If both results are the same, so therefore, inshallah, our method is correct. So that's what our approach in this particular problem solving. So I'm going to put a statement here: recall Biot-Savart. Okay, so we're going to recall the problem that we solved under Biot-Savart. So what we managed to do, we said that the H along the axis of the solenoid is equal to what? Anyone remember? What is our H? Okay, you have to look back in your solution. Yes, we did say that the field is along the z-axis, and then number of turn multiply with the current, and then we divide with 2L because we cancel the 2 pi, and then we have Z over square root of A squared plus z squared, that should be one term, minus, then we have the second term given as z minus L, divide everything with a squared plus z minus L squared. Okay, and then we said that the unit for this H is ampere per meter. And it seemed to us the solution is quite lengthy and cumbersome. So now let's adjust this general solution to our task here. So what we need to determine now, find H in the region center of the solid. So meaning let's assume that you want to find H at the center of this solenoid. So it should be the middle point here. So we know the bottom face of the solenoid is located at z equal to 0. The upper face of the solenoid is z equal to A. Therefore, the middle point or the midsection part of the solenoid should be z equal to L over 2. So let's say at the center, so we are saying that z now is equal to L over 2. We specifically adjust the general solution to be at a specific point. Why? Because the question asks us to determine at this position. So we are adopting the general solution to the specific task by giving the z value to be L equal to 2. So now our H will be equal to what here? H, you need to substitute only z and I over 2L. So the first substitution should be L over 2, divide everything with square root of A squared plus L over 2 squared minus L over 2 minus L, divide everything with square root of A squared plus L over 2 minus L, everything squared. Okay, so let's solve the mathematics. So now becoming negative L over 2 here. So negative with negative becoming plus. So plus, now L over 2 plus L over 2 will become L. Okay, that's going to be the upper part of this fraction. And then this one L over 2, now L over 2 again, they are the same. So I'm going to make it simple, simplify the mathematics to become Z and I over 2L. Okay, now the upper part now will become L, correct? Because L over 2 plus L over 2, divide everything with square root of A squared plus L squared over 4. Okay, that should be our simplified version of the upper part of the mathematics. Now let's make it simple. So now I'm going to take out the L over 1 over 4, and then I'm going to put it up here, and then I'm going to cancel out. So after cancellation should be Z and I. Okay, this one will become 2L. So now it's become 2L, divide with square root of 4A squared plus L squared. Correct? So now let's simplify further. I'm going to cancel the 2 pi with 2 pi. Okay, so this is 2L with 2L. So now we're going to have this as our solutions. Okay, which is Z and I over square root of 4A squared plus L squared. Okay, so now we're going to go back to the definition given by the question. Since L is much greater than A, okay, that's what we're going to put into our solutions. Okay, since L is much greater than A, okay, so now our H will become what? Okay, Z. So now this term L is much greater than A, therefore we can ignore this 4A squared, so it become only L squared, and then square root, so we're going to have the final solution to be N I over L. Okay, that should be the magnetic field intensity in the center part of the solenoid, using Biot-Savart law. Yeah? So now let's use ACL to solve this problem. Okay, let's do it now. Yeah? Okay. Using ACL, that's what our objective here. Using ACL, Ampere Circuital law. Okay, let's recap the steps that we need to follow through using ACL. Okay, the first step should be, what should be the suitable coordinate system? So we know that it's going to be a cylindrical. The second point is the point of interest. We're going to define that later. And the third part is that we need to draw the current either coming out or going into the paper. Remember? So let's do that. So what I'm going to do here, okay, so if we go back to this diagram, I'm going to cut longitudinal. Okay, I'm going to cut this solenoid longitudinal so that the current going to be either coming out or going into my paper. So therefore, in 2D, the same diagram going to be appearing as such. So I'm going to draw the z-axis first. Okay, that should be my z-axis. Okay, so now since our solenoid is infinite, I'm going to draw dotted line. Okay, that should be referring to one side of the solenoid and then another dotted line. So what should be the radius here? Okay, the radius should be equal to A. Okay, and then what we're going to see, the current of each turn going to be as shown here. So going to be, this going to be what is the pattern of the current appear in my 2D diagram. Okay, number is n turn. So and then we have the same current defined as such at the bottom of my cylinder here. So dotted here indicate infinite. So what should be the configuration of the current? The current flow in phi directions. Okay, in phi directions. So meaning coming out, going into, correct? Coming out from paper, going into the paper. Coming out from this paper, going into, and you have to repeat that. So therefore, seems to us, the upper part of the solenoid, the current are coming out, whereby the lower part of the solenoid current is going into. So that should be the conclusion of what we see, and then we define that as such. Yeah? So now, what appear to us now, so the current density given as J, okay, so coming out, since this is a surface current or volume current, yes, this should be a surface current because it appears just to be as a surface. So I'm going to define surface current there, okay, going into. So therefore, this should be our simplified version of our problem by focusing on how the profile of the current in this problem. So the concern here, we need to redraw the current configuration either coming out or going into this paper. So in this case, this is what we're going to have as the simplified version. See, going back to point 2, so I'm going to define now the first current I'm going to, the first field I'm going to determine located in the outer region. Okay, so therefore I'm going to define based on ACL. The outer region defines region number 1. the lower region defined, sorry, the inner inside the cylinder defined region number 2. That's what should be our region of concern. Region 1 located outside the solenoid. Region 2 located inside the solenoid. So we have two distinct regions. So therefore, I'm going to focus on region 1 now. Okay, region 1. So what we're going to define here, R should be greater than A. Okay, that should be our focus now. So we need to draw our Ampere circuital loop, remember? So what should be the logical shape of our Ampere circuital loop based on our experience? Because this particular structure is, source is a surface current. Therefore, what we did before in our example, we going to select that our Ampere loop to have a rectangular shape, because that's what we did before. I'm going to take it to be, this is our first loop line, second loop line, because why? Remember, ACL must pass through the point of interest, and then the second point, the loop must be what? Close, completely close. So I'm going to make it like this. Okay, so that should be our ACL. Based on this particular region. It seems to us that the box is large. Actually, this is part of our diagram. Remember, we assume the length of this solenoid is very, very long. Okay, due to that reason, actually, our loop, which is Ampere loop, is small. But due to the nature that we draw as such, we exaggerate that our loop look large. Actually, is small. Okay, now, so let's go to the next step. Remember, ACL, first coordinate, we've done that. Second region of interest, we are doing that now. Third, we're going to, okay, we've done that, draw the Ampere loop, we have done that. And then the next continuous step is actually solve the mathematics. So, using ACL equation. Okay, what does it say? H dot dl should be equal to I enclosed. Remember, H dot dl always based on the shape of the loop. I enclosed going to define as the current confined by the loop. Okay, I'm going to focus on the I enclosed straight away. Okay, what I'm going to see now. So since the length on the upper part of the loop is similar to the lower part of the loop, and then another condition, the surface current in terms of magnitude actually the same in the upper surface current as well as the lower surface current. But what we can see, the configuration, how the current flows. In the upper surface current, the current coming out from the paper, correct? Whereby in the lower surface current, the current going into the paper. Therefore, the net current going to be this current plus with this current. But yet, due to the way the current flows with regard to the surface, coming out, going into, therefore, we're going to subtract them. Therefore, the final solution for the I angle going to be 0. Okay, so what we can say, for outside the region, our magnetic field H1, which is focusing on region number 1, is equal to 0. We're going to detect no magnetic field outside the solenoid. So that should be the first observation. Okay, so now let's go to the second observation, region number 2. Okay, so region number 2, I'm going to make it proper here, region number 2. So here focusing for R smaller than A. That's the condition for region number 2, R smaller than A. Just to make the problem look at it, I'm going to redraw my current profile again, just to make sure we see it clearly. Okay, the upper, I'm going to make it as coming out. Okay, and here is going into. Okay, that should be the profile of current. So now our concern here, I want to find my H to be located in this region. Okay. So there are two ways of doing it. One, we're going to repeat with the same method that we have done up there. So first, by doing what? Draw our loop. So I'm going to draw. This should be my first loop due to the upper current source. And then another loop going to be due to the lower. So therefore, it's going to be like this. Okay, so therefore, this is the way we're going to define, because the H here, okay, I'm going to put the H in the region number 2 should be defined as H contributed by the top loop plus H contributing by the bottom loop. Okay, that should be what we're going to state here, because we can see at this point there are two fields. One coming from the upper current source, and the second field contributed by the lower current source. Therefore, what we're going to say, H in region number 2 is due to the summation of H top plus H bottom. Okay, we can do H top by repeating the mathematics shown up here as one method, meaning that I have to solve the mathematics for the upper Ampere loop and then get the solutions, and then I'm going to repeat for the lower Ampere loop and get the solution, and then we add them together. It's quite cumbersome. So now we're going to use our experience again, because that's what you can see in EMT. The more example you did, the more method that you can use to solve your problem. So instead of doing that, I'm going to use another method using standard solutions of infinite surface current. Okay, so have you seen that equation? Yes, where H here is equal to half Js cross An. Remember that equation that we discussed before? So that should be my method here, rather than repeating the above method individually and then sum them together. I'm going to use the standard solutions. So therefore, I'm going to state now H top going to be half Js cross An. So remember the way we define Gs from the bio-Savart? Yes, total current divided by total length. So I'm going to state it to be half. What should be the total current on each side of the solenoid, Ni? What should be the total length of the solenoid, L? How the current flow in phi directions. Okay, that's how we define the Gs cross. Okay, for the An, the way we define An, remember, must be from the current unit vector to the location of our H. This is our An now for the upper current source. So what should be the unit vector for that unit An? Okay, should be negative R. Going into the z-axis, okay, positive R coming out from the z-axis, negative R going into the z-axis. From outside going into the z-axis, therefore the unit vector should be negative R. So what should be the solution for cross vector, cross unit vector phi cross negative R? Okay, phi negative R, yes, it should be Z. Okay, so therefore what we state here, the solution will be equal to N I over 2L in Z directions. Okay, that should be the solution. I mean, quite simple here, you see, rather than we do the mathematics of H dot dl, then choose path and then substitute and then integrate, put the limit and then get the solution. But here just by using standard simple infinite solutions. Okay, similarly, we're going to define now H bottom. Okay, H bottom now. Going to be half JS cross AN, and then I'm sure if you do it properly, it's going to end with same solution as what we obtained above. Yeah, so therefore that should be our solution. Now if we put back that solution into our main definition of H region 2, what should be our H region 2 now? Should be this equation, correct? Plus with this equation. And then what going to be the solution here? Good. And I over L in which direction? Z directions. Okay, that should be the solution using ACL. So let's compare with what we have obtained using Biosawat. Okay, and then alhamdulillah, you can see clearly the final solution for both methods are the same. So therefore, this is going to be acceptable because they end with the final results. Okay, there you are. Okay, that's how in EMT, you never doubt your method because you can verify your solution using different approach. But yet, if the solution ending with the same results, that's confirmed that the selected approaches are correct. Okay, that's what you have to always do in real life engineering because you need to verify. You always have to compare results. Not only accept by doing one approach, your method is correct. It's not acceptable approach. Okay, shall we do one more example? Okay, I'm going to do one more example now. Example number 5. I'm mistaken. Okay. Example 5. Okay, what is the common structure that we have seen a lot in our EMT syllabus that you can state here? Okay, I think this should be quite common for us. Solenoid. Correct? We have seen solenoid in a lot of cases. Okay, when we talk about capacitance, resistance, and then potential difference, energy stored in electrostatic, all involve a lot of solenoid problems. So now I'm going to use that as my basic structure in example 5 problem. Okay, so let's say you have a solenoid now. So let's draw a solenoid. Solenoid consists of the inner conductor. Okay, that should be the first conductor, and then you have dielectric material, and then you have another conductor. Okay, that should be our second conductor, having the same axis as the inner conductor. Okay, that should be typical solenoid. Okay, so let's give dimension for solenoid here. The inner radius, let's say as A, and then the inner radius of outer conductor defined as B here, and then this particular I'm going to define as C. Okay, that should be our solenoid dimensions. So assume infinite. Why? Because we want to use ACL as our approach here. So therefore, we have to assume this solenoid as infinity. So therefore, infinite, we have to add this extra information in our diagram. So that's indicate now the problem dealing with infinite structure. So what should be our objective here? Find H in all region. So that should be our problem. Find H, which is magnetic field intensity in all regions. Okay, so that should be the method. Sorry, that should be the problem. Now let's proceed now solution wise. Okay, solution, I'm going to put word solution so that you can see we're going to focusing on the solution to this problem. Okay, so since the structure is infinite, using ACL, since the solenoid is infinite. If the solenoid is finite, we cannot use ACL, we must use Biot-Savart law. And then as you can see, it's going to be cumbersome mathematically, but yet can be solved inshallah. Yeah? Okay, so now ACL is our focus now. So now we have to go back to the steps involved in ACL. Good. First, coordinate cylindrical. Second, we know that it's going to be how many regions in this particular problem. Good, 4 regions. Region number 1, region number 2, region number 3, and region number 4. That should be 4 distinct regions that we need to consider in this problem, because we have to find H in all regions, all possible regions. Therefore, from this diagram, we're going to conclude there are 4 distinct regions need to be solved here. Yeah? Okay, now we're going to focus for region number 1. Okay, so for region number 1, I'm sure we have done it before. And then this is the case for R smaller than A. Okay, that's your region. So based on our previous example, what should be our H in region number 1? Okay, H of region number 1 should be equal to I R over 2 pi A squared in phi direction. I think you can remember that solutions when we solve example 2 problem of ACL. Okay, so refer to that example. Inshallah, you're going to see it's ending with the same solution as shown here. Okay, for region number 2, this is true for the case of A smaller than R smaller than B. Okay, in this region. So I'm sure you can also refer to example 2 that we have solved together, and this end with I over 2 pi R phi directions. Correct? Okay, therefore, so these 2 regions defined from example 2 solutions. So I'm going to go for region number 3 now. So this is new now. Region number 3. Okay, this is true for a case B smaller than R smaller than C. So this cannot be referred to anywhere because this is totally new. So we have to repeat the basic method of ACL. So I'm going to draw the current. Oh, by the way, we haven't defined the current yet. Sorry. Yeah. So the way the current behave in this problem is such that the inner conductor having total current I shown, and the outer conductor having total current I in the opposite directions. Yeah? So that is also total current I. Okay, that should be the way the current flows in this problem. Inner conductor having total current upward, whereby the outer conductor having total current flow downward. Okay, so I'm going to draw now my 2D based on how the current flow. So we're going to show this is the inner conductor. This is going to be the outer conductor. Okay. So inner conductor coming out, the outer conductor going into. This is how we profiling the current flows. Total I, okay, and then let's so that's done. So this radius A, radius B, radius C, okay, that's what we, okay, now, so what we have to do for this particular problem, we want to find the H located in region number 3 between B and C. So I'm going to define that clearly here. So this is my point of interest. Why? Because it's located between R equal to B and R equal to C. So therefore, that should be our focusing point for solving this region 3 issue. Okay, that's defined. Now we need to draw our profile or ACL here of our loop. Now we're going to, based on experience as well, we're going to draw the loop to be a circle. Okay, and then the radius of our loop here going to be R. And then you can see it's agree with the definition of region number 3. Why? R is located between B and C. So that is reconfirm our definitions. Okay, now I'm going to solve the mathematics. Okay, so mathematics state H dot dl equal to I enclosed. Based on our previous experience, the solution for the loop circle going to end with HV multiplied with 2 pi r. Okay, that should be the standard solution now we're going to take whenever we see this type of loop structure. Now the I enclosed going to be whatever current resides in the loop. And from this diagram, we can see there are two types of current. One current is located in this region, correct? Okay, this is current inside the loop. Another current is the one that located in the outer conductor, but only part of it. It's not all the outer conductor. It's a part of the outer conductor as shown. So therefore, what we can see, the current here going to be this current as well as this current. So I'm going to set now I due to the inner current, and then I'm going to sum. But since the current configuration are not the same, since I assume this current to be in positive sense, therefore this current need to be represented in negative sense because it's opposite to the one that we define positive. Therefore I'm going to minus here I. Okay, let's make it nicer. I'm going to define this to be my I, and the blue I'm going to define to be this particular current. Okay, that's how I'm going to define. Yeah, so I, this current, and this I, this current. Why? Both current located inside the loop. Now, for the second term now, I'm going to solve the mathematics now. Okay, should be integrations of J, because it's volume current, remember, dot with ds. Okay, that's how we take it to be, because we can see when the area change, this current value also change. Therefore, the S should be our suitable substitution. Okay, what should be the J now defined as? Okay, the J I define to be total current divided with what? Total area. And I'm going to give the direction to be, let's say Z here, Y, because negative is already put in front here. Okay, if you put it negative Z, it should be plus here. So this, since we already set it to be negative here, I'm going to just assume my J to be Z here. Actually, when I put negative Z, is going to be defining what we actually see in this diagram. Okay, that should be our, so what should be total current now in the outer region? Yes, I. And what should be the total area that you can determine in the outer conductor? Good, should be pi C squared minus B squared, correct? That should be our total area, Z directions. Okay, that's done. Now, what should be our ds? Our ds should be r dr dv in Z direction as well, correct? And now we have to have limit, double integrations. For the r, should be from where to where? R should be from the shaded region B to R, okay? B to R, and for the phi 0 to 2 pi. Okay, so now let's substitute everything up here now. So what we're going to have now should be I minus I bracket. Okay, so now R minus B, R square minus B squared, that should be, and then divide everything with C squared minus B squared. Okay, that should be the I enclosed. Okay, so when you simplify the mathematics, what we're going to have here is equal to I. Okay, so now the C, so the B cancel, should be C squared minus R squared. That should be, divide everything with C squared minus B squared. Okay, that should be after you simplify further. Okay, that should be the I enclosed now. Okay, so we need to find the H. So what we have to do now, H number 3. Okay, therefore H3 now will be equal to I C squared minus R squared over 2 pi R C squared minus B squared. In which direction? Phi direction. Okay, that should be our solution for H region number 3, based on proper ACL. So what we can see now from this particular example, the direction how the current flow is crucial. When the current flow in opposite direction, you have to take action on that. So when the current flow in the same direction, you have to consider that as well, because the way the current flow actually going to affect your final solutions. Okay, that's for region number 3. But yet, as what we have stated before, in this problem, they're going to be how many regions? 4. So I'm going to go for the last region, region number 4. Okay, so region number 4, we're going to put it here because we still have space here. Okay, region 4. So what is the characteristic of region number 4? R is greater than C. Okay, that should be region number 4. Okay, so in region number 4, if you see from these equations, okay, now our loop located in the region number 4, and based on this equation, what we can see, we've seen the current flow given by the question having the same magnitude, okay, whereby the inner conductor having total current I, and the outer conductor having magnitude total current I. Therefore, since their current flow in the opposite direction, therefore the net mathematics on this right hand part of the mathematics equation going to be end with 0. So therefore, what we're going to call or state now region number 4, and with the H equal to 0 ampere per meter. Okay, So there you are. So now we have completed examples regarding biosawat that you need to understand. This basic example. From here, additional complexity can be added. So I think it's enough for us to discuss basic concept here. And then inshallah in my next lecture, we're going to go through all the topics stated by our syllabus. So with that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.